This video is all about defining vector components and how to find the components of a vector in the direction of another vector. And I'll give you a hint, spoiler alert, it all has to do with the dot product. So I hope you can remember all about the dot product. We're going to use that over and over again to find components of one vector in the direction of another vector. So a component, when I say that word component, what I'm meaning is a piece of a vector. It's the projection of a vector in the direction of another vector. So in the previous video about dot products, I kind of showed it as a shadow. It's like if you shined a light on a vector in a particular direction, you would create a shadow. And that shadow is also known as the projection of a vector in a particular direction. So to find the component of a vector in a particular direction, it's going to involve taking a dot product. So let's do an example. It's easier to kind of explain this in terms of an example. Let's say I give you these vectors here, vector f and vector m hat. And I asked you, what is the component of vector f in the direction of m hat, the m hat unit vector? What you need to do in order to find the component of f in the direction of m hat, that is equal to the dot product between vector f and the unit vector m hat. And then you do that dot product and you multiply your result by the direction that's defined by m hat. So that's the prescription of how to find a component of a vector in a particular direction. You do the dot product between that vector with the unit vector in that direction, and then you multiply your answer by that unit vector. So using our definition of the dot product between any two vectors at all says that you take the magnitude of the first vector, you multiply it by the magnitude of the second vector, and then you multiply that by the cosine of the angle between them. So in this example, the angle between these two vectors I labeled as angle theta. Always draw your vectors tail to tail and then identify the angle between them. So I just kind of copy this down. Instead of writing the dot product, I fill in the definition of the dot product. One more simplification I can make is that m hat is a unit vector. So m hat, the norm of m hat is just the number 1. Unit vectors have a norm or magnitude of the number 1. So the next thing I could write, I could kind of basically, I don't even have to write norm of a unit vector. It's implied that it's the number 1. So really, the component of vector f in the direction of m hat is the magnitude of vector f times the cosine of the angle between f and unit vector m. And then I do that and I multiply it by m hat. That is the component of f in the direction of m hat. And like I said, when you're doing a projection or finding a component, you can kind of imagine shining like a flashlight on this vector and looking for the shadow that emerges. So I'm shining my flashlight towards the direction that was defined by m hat. So this line here defines this direction of m hat. I shine my light on my vector f, and I should see a component emerge. The shadow that emerges, that is the component or the projection of f in the direction of m hat. Notice here that this green arrow, this component, is pointing in the opposite direction as m hat. And that kind of tells me that it should signify in my brain that I should be getting a negative sign. When I get this component, there should be a negative sign associated with it because it's pointing in the opposite direction as m hat. And if you notice there in my expression for my component of f in the direction of m hat, I see that cosine theta. And if you look at my angle theta, it's definitely an angle that's bigger than 90 degrees. And so when I take the cosine of that, I'll get a negative sign in the end. So don't be afraid when you get negative values for vector components. That's fine. That just tells you about the directions of those components. So you may have noticed I I'm a little bit vague in that previous description of vector components about what a component is. And I want to now take a little bit of time and define. There's something called a vector component, and then there's something called the scalar component. And technically, when you say the scalar component, you're describing the scalar component of the vector component. So in that previous slide, I said that just the component of F in the direction of M hat. I was not very specific on what component I'm talking about. I said that it was equal to the dot product between F and M hat times unit vector M hat. So what I've actually given to you here is the vector component. So all of that stuff, the dot product between vector F and M hat, all of that times M hat, that's a vector. The dot product is a scalar. But when you multiply it by that vector M hat, you have now created a vector quantity. So all of that stuff that I have in the green bubble right there, that is technically the vector component of F in the direction of M hat. So I really should be more specific, and I should say the vector component of F in the direction of M hat. What I have within that vector component expression is the scalar component. So the dot product, if you remember, produces a scalar. So when you take the dot product between F vector and M hat, you will get a scalar out. And so the scalar component is a piece of the vector component. So it's the scalar component of that vector component is just the dot product between vector F and M hat. So whenever anybody asks you for the component of a vector, you should ask them, are you referring to the vector component or the scalar component? Most of the time, they're going to be asking you for the scalar component, but you should ask them to be more specific, because technically that phrase component, it's not very specific whether they're speaking about vectors or scalars. So they should be more specific, or you should ask them to be more specific. I will try to always be more specific. So let's look at this. What's really the difference here between the vector versus the scalar component? The scalar component is a piece of the vector component. So the scalar component of vector, sometimes we'll use an abbreviation instead of always writing it in terms of a dot product. We'll abbreviate it, instead of writing F dot M hat, we'll abbreviate it as the name of the vector F, and then we'll give it a subscript. And that subscript tells us the unit vector or the dimension that we're trying to find the component in. So in this case, I was trying to find the component of F in the direction of M. So the abbreviation, instead of saying all of that over and over again, I could just abbreviate it as capital F sub M, where that F is the name of the vector I'm looking for the component of, and M is the direction that I'm trying to find that component in. So that's a common abbreviation you'll see over and over. And so we already said that the vector component is made up of the scalar component times the unit vector in the direction that we were investigating. So really, you could also abbreviate that as well. Again, instead of writing a dot product and multiplying it by the unit vector, you could just use this abbreviation of the scalar component and then multiply that by the unit vector instead. So this abbreviation I just kind of brought down here. So the vector component is always the scalar component times the unit vector. And the scalar component comes from the dot product of the vector with the unit vector that defines that direction. All right, so let's do an example. Let's kind of let's do an actual real example here and see how we can use all of this information and apply it to a problem. So here in this problem, I have a kite that's flying in the sky. It has a velocity vector v. That velocity vector has a norm of 2.76 meters per second. Wind's blowing on the kite, there's a string pulling on the kite, there's the gravitational field of the earth is also exerting a force on the kite. All of these things combined cause an acceleration for the kite. So the acceleration of the kite is just vector A, and that norm of vector A is 7.75 meters per second squared. So I have two vectors, vector V and vector A. I'm going to tell you what those look like. I showed you some directions, some angles relative to a vertical line. And your goal for this problem is to figure out the component of the velocity vector in the direction of the acceleration vector. And after we do that, then I want you to find the component of the acceleration vector in the direction of the velocity vector. Okay, so those are our goals. I drew my two vectors. Now let's use those definitions of how to find components. And you can see that I have already started being vague about these components. Let's find the scalar components of each of these vectors in the direction of the other vector. Well, maybe actually I wanted you to do vector components, sorry, vector components. So let's start off with part A. We're going to find the vector component of the velocity vector in the direction of the acceleration vector. So what I want is I need to take the dot product between the velocity vector and the unit vector in the direction of the acceleration vector. I'm going to do that dot product and I'm going to multiply it by the unit vector of the acceleration vector. So let's draw this, okay? I want to visualize these unit vectors. So the velocity unit vector points in the same direction as the velocity vector. It just has a norm of 1. Same thing with the acceleration unit vector. It points in the direction of the acceleration vector. It has a norm of 1. So let's use the definition of the dot product and just kind of plug that stuff in. So over here for the vector component of V in the direction of A, I need the dot product between V and unit vector A. So I plug in the definition there. The definition of the dot product says the norm of the first vector times the norm of the second vector times the cosine of the angle between them. What is the angle between these two vectors? Because I see that angle pop up. I'm going to need that vector or that angle in both of these parts of the problem. So let's redraw our vectors tail to tail, and we want to identify the angle between them. Technically, I like to find the smallest angle between them. So in this picture here, I would see that is angle theta. So to find angle theta, we need to do a little bit of geometry. If those two angles are defined, I see a 70-degree angle. That means that this little piece right here must be 20 degrees because I know the 70 plus 20 has to add up to 90. And likewise, near the acceleration vector, I see one angle is defined as 50. That means that that piece right there must be 40 because I know 50 plus 40 adds up to 90. So angle theta is equal to 20 plus 90 plus 40 degrees. So angle theta, I would say, is actually 150 degrees. So now that I have identified angle theta, now I can plug that into my expressions here. And I can also use the definition of the norm of a unit vector. I can replace, so over here, I know the norm of the velocity vector was 2.76 meters per second. The norm of unit vector A is just the number 1. And then I have the cosine of 150 degrees. And all of this stuff is being multiplied by unit vector A hat. So now you can actually plug stuff into your calculator and get a number out. I get 2.76 times the cosine of 150 is negative 2.39 meters per second A hat. And that is the vector component of the velocity in the direction of the acceleration. Now let's do the other piece. Now I want to find the vector component of the acceleration in the direction of the velocity. So now I'm doing the dot product between vector A and unit vector V. So I can use the definition of the dot product. That's going to be the norm of vector A times the norm of V hat times the cosine of the angle between them. And then all of that stuff gets multiplied by unit vector V. So now let's plug in some numbers here. I know the norm of the acceleration is 7.75 meters per second squared. The norm of a unit vector is just the number 1. Again, I have the cosine of 150 because that's the angle between the A hat unit vector and the velocity vector, and the velocity hat unit vector and the A vector, like those are in the same directions. All of that is multiplied by unit vector v. So again, now I just plug in some stuff in my calculator. And I get negative 6.71 meters per second squared. And those are my two components. So I hope that that example kind of showed you the method of finding the component of a vector in the direction of another vector. You might be asking, why in the world do we want to do this? Well, the reason that we're going to do it over and over again, mostly for the rest of the semester, is that it's really hard to draw vectors graphically and do it accurately. So the method that we had been using with like kind of using grids and lining up our vectors on a grid and counting squares, that just doesn't work if your vectors don't line perfectly up on the grid. And grids just don't really exist in the real world. Like we measure angles instead of measuring lengths. So we're going to have to start using these vector components to express our vectors in terms of other unit vectors. So this is what we're going to do for the rest of the semester, is working on finding the components of vectors in particular directions so that then we can mathematically manipulate those vectors using rules of vector math. All right, so that's why we're doing it. Get used to it because we're going to do it over and over and over.